Hi everybody, Dr. Painwell here. We are going to talk about constructing groups. This is kind of properly classification and cluster analysis. Um, the idea here is generally from quantitative data, at some point we're going to want to classify that into groups or types or named things. And we're going to talk a little bit about how you do that in general cases, but also in a geographical context. So what have we done so far? We've talked a little bit about t-tests and ANOVAs and non-parametric extensions to these. We've talked about regression. Most of the time here, so in t-tests and ANOVAs, we're looking at, we have groups and we're trying to figure out if they're different according to some quantitative variable. Are the rats that I gave the growth term to any bigger than the rats that I didn't give them to? Is the Western United States have higher unemployment on average than the Eastern United States? Regression, we're trying to relate to quantitative variables. If I am this tall, can I predict with what accuracy how much I weigh? In this case, what we want to do is we want to take some quantitative variable and we want to guess its category. So there are lots of different ways of doing that. We're going to talk about a few. I'd love to be able to talk about self-organizing maps, but we just don't have time. So we're going to focus on discriminant analysis, measuring how well one of these kinds of analysis works, k-means clustering, principal component analysis, and random forest classification. So we're going to move through these next slides pretty quickly. Maybe a bit belaboring this point here, but geographers, they really, they break things down into groups and regions. And sometimes those categories are fuzzy. So this is one of my favorite examples. How many oceans are there in the world? I actually grew up learning 4. It sounds like plenty of people learned that there are 5. The 5th one is the Great Southern Ocean. But you could also think of this as one, right? Now it's all connected. How do you divide up the oceans, right? It seems kind of a fuzzy thing, and sometimes it is. It can be difficult to draw the lines for these regions, whether it's an ocean or otherwise. How many continents are there? Most of us learned 7, but Europe and Asia are divided by the Ural Mountains. That's pretty arbitrary, right? You could just call it Eurasia, and some people do. And in fact, Africa is connected as well, so maybe we want to throw that in there. North and South America are connected. So the point of this is there are lots of different ways to slice these things out. Which states are in the Midwest, right? That's in the Midwest or out of the Midwest is a category. Sometimes it's difficult to decide whether it's in or out. Is Missouri in the Midwest? Is South Dakota? So we'll just look at a couple of cases real quickly here. We'll move through quickly so we can kind of get to the meat of the lecture. This is one way that the world is often divided up, core and periphery. What goes in there may be debatable, but kind of in that group or out of that group is not so uncommon. But again, where do you draw this line? I grew up on this 3 worlds theory. First world is the United States. And its allies. The second world was the USSR and allies. It's actually kind of interesting because these days, since the fall of the Soviet Union, people don't even really remember what the second world is anyway. They use first world, they use third world sometimes, but they hardly ever use second world, which is fascinating. And of course, if you take a world regional geography class, you'll find the planet kind of carved up into these different regions. There are lots of ways of doing that. Here's one. Here is another. Here's the United Nations classification. That can be further subdivided. So these are the United Nations subregions. These are the census regions of the United States. So we've got a couple of big ones, and then those can get divided up into smaller ones. This is one of my favorite. So dividing the world up into metropolitan areas. So if we just sort of regard cities as the centerpieces of the area around them, sort of a hinterland kind of conception of space, and we picked these cities, what would be the regions that would define them? So this is one kind of out, this came out a few years ago. There are a couple of different versions of this, but this one is actually probably the most directly relevant to what we're talking about today. These are some fun ones. So these are also algorithmically determined. If America were 3 states of equal population, so we could use something like a rasterized population layer that we could get from NASA CDAC or some other place, and carve this up. This is correct in the sense that these, you can see the little statement of accuracy, populations are within 0.002% of each other. I'm sure that's true. However, you could divide this up. The way that the algorithm does this is quite flexible. So you can see there's sort of an attempt to divide things up along roughly north-south lines. Remember that this is a conic projection, so the lines that you're seeing there aren't exactly parallel. But the attempt is to sort of draw these big things, and then the computer can iteratively decide where the edge cases go to balance things out. But there's no reason why you'd have to do that. You could do that in any orientation, right? You could divide things up into 3 pieces along north-south axis lines if you wanted to. So totally arbitrary, still kind of fun. This is people like to click on this stuff. And there are several versions of this. I'll just quickly go through them. Here's one with 4. Here's one with 5. Here's one with 13. This is a similar kind of a deal. If the United States is divided up into congressional districts, which are fundamentally categorical, nominal groups. How do we do that? Well, other than obviously assuming spatial contiguity, which is important for all of our algorithms, essentially you can just sort of have the computer sort of decide, if I put this pixel here, this pixel there, it can figure these things out pretty easily. So this is kind of a classic one. Computer programmers solved gerrymandering in his spare time. As a geographer, this stuff comes off as completely ridiculous to me. It's not that you can't apply algorithms to improving these kinds of results, but why, the question here, why do people need to be involved in mapping the districts? There are really good reasons why people need to be involved in mapping the districts. Just because an algorithm spit this out doesn't necessarily make it a good solution. These are current congressional district boundaries. This came out of 538, which is probably a slightly better version of this computer solves the gerrymandering problem example. These would be examples of redrawing that to produce highly competitive districts. And I want to emphasize that these approaches are probably a little bit more valuable than computer programmer solves gerrymandering in his spare time, which don't take into account the political complexities of this stuff at all. Okay, so we're going to get through some of this stuff. What I want to talk about first is some non-spatial applications of this stuff. And your question rightly might be, what does this have to do with me? I'm a geographer. I want to use GIS to solve these problems. Why do I need to know how this stuff works? Well, the geographic stuff is basically an extension of the non-spatial stuff. So we're going to learn how the non-spatial stuff works. I'll show you an example of how it applies to spatial geographic stuff. But knowing how kind of the underpinnings work, and we're not even going to get into the math of all of this stuff, but we are going to sort of see how this works in a non-spatial context. The other things that I would say is that geographers sometimes get hung up on the fact that space is autocorrelated, which is totally true. It definitely is. Nearer things are more related than distant things, all other things being equal. But so is time. Time is autocorrelated, and geographers pretty uniformly will ignore that in their analysis, which is fascinating. But the more you have a grounding in sort of the general techniques, the better off you're going to be. Let's take a look. So there are lots of examples of this. Again, the idea here is classification. Another way to put this is going to be dimension reduction, finding groups from different variables. We'll get into the details of that as we go. But here's an example. This is one of my favorite things. You know, you'll often see these things kind of floating around social media. I guess I haven't seen them in some time. But people will sort of say like, I'm a this, I'm a that, and basically they describe themselves as a personality type related to these, what break down to 4 different binary variables. So the the E versus I extroversion introversion axis, sensing versus intuition as another axis, thinking versus feeling as another axis, and judging versus perceiving as another axis. So the idea here is that based on these divisions, these simple sort of binary things, you can determine somebody's personality type, sometimes referred to as the Myers-Briggs types, to kind of come up with your personality based on these variables. And if you run all of the combinations, you get 16 of those. Another way of thinking of this is the big 5 personality traits. So this one's a little bit more, the Myers-Briggs is sort of not really super well regarded within sort of the scientific psychology community, but the big 5 is more so. And so what they would say is that a lot of the traits, a lot of the personality traits that people have, you can sort of reduce to openness, conscientiousness, extroversion, agreeableness, and neuroticism. These are ways to sort of refine that data down to take a lot of different variables that you would think people can differ on and sort of aggregate them into these kinds of things. So these are all attempts to sort of take a lot of multidimensional data and to sort of cluster it together into smaller, fewer pieces. This is kind of one of my favorite examples of this. This comes from 538. There's a number of these I'll show you in a second. These are the quote, the 4 types of Tom Cruise movies organized by Rotten Tomatoes rating and box office gross. So 2 dimensions of these movies out of, you know, potentially hundreds of dimensions, but reasonable ones, right? Like, what did people think of this and how much money did it make? And if you do that, then this particular author has by hand drawn little boundaries around these things. So you've got sort of really high regarded, high box office movies like Top Gun would be the classic. You've got sort of really highly regarded, but sort of, you know, they make good money, but not amazing money, like Jerry Maguire. You've got sort of middle of the road stuff that you know, Tom Cruise is able to pull in good ratings and lots of money, you know, which is about what a normal movie is. And then he's been in some stinkers just like every other Hollywood actor. There are lots of these. These are great if you have a minute to kind of look these up. This author, Walt Hickey, has done a good job of sort of replicating this a number of times. People must be clicking on these things, and I certainly have. But the attempt of that is basically this, right? To take multidimensional data set and say, this all boils down to 2 types of movie, or 3 types of movie, or 4 types of movie. How is that done, right? So Walt Hickey sort of does it with a marker, right? Just sort of plots these out in a couple of axes and then draws lines with a Sharpie effectively around these movies and then makes up names for them. That's fine, that's great. How do we get a computer to match that kind of human intuition, to process that data in a way like we would process it to come up with these groups? So one of the ways we can start approaching this is with the classic Fisher's iris data, which we've seen many times, a very famous data set. We've used it before, and you can find a link to that in the course data, or frankly, all over the place online. So if we access that, we load it into a pandas data frame, and we just create a scatter plot with Seaborn. So Seaborn, one of our favorite data visualization packages. We call seaborn.scatterplot, we pass it our data frame, and we say, well, let's look at petal width and petal length, and I want you to color it by species. And you get a plot that looks like this. So we have, we're looking at petal width versus petal length, and if we color these by species, you can see that they pretty clearly come out in a couple of 3 different clusters. Pretty easy to see. And so we know, or we can sort of say with some certainty that species really does matter here, right? They're not just all intermingled. Species hang together differently, which is what we would expect, right? Sort of part of the way that we define species originally was sort of their morphological manifestation, right? What they look like. And later we start using things like DNA and genetics to help us refine those models. But mostly we can kind of look at a lion and look at a tiger and say, well, those things look pretty different to me. I think they're two different things. And that's essentially all we're really doing with this kind of classification. These two things look kind of different to me. I guess they're two different things. So in the last plot, we looked at sort of plotting two variables against one another. One of the nice things about Python is we've got some pretty easy capability to actually add a third dimension here. So now we can look at how petal width and petal length and sepal width all relate. Obviously past 3 dimensions, humans have a hard time visualizing this, although we could certainly add the 4th one and animate it in time if we wanted to. But generally what you're seeing here is now we can sort of look at how these things cluster in 3 dimensions. And you can sort of see the relationships between the different species here. So the kind of classic approach to doing classification is called linear discriminant analysis, and it's essentially just a kind of a regression. Instead of guessing a quantitative variable off of another quantitative variable, we're using a quantitative variable to predict a categorical one. So if you're interested in this stuff, you may also want to see logistic regression and probit regression for examples of the reverse of this process. One of the things I think that's confusing for students is there's all these different kinds of regression. Oh, I've never done a logistic regression before. I've never done linear discriminant analysis. These days, a lot of that nomenclature is starting to kind of fade out a little bit. I'm using it here because it's still pretty common, but increasingly people are using general linear models to describe these things, because ultimately the way that these things handle categorical versus quantitative versus numerical kind of data in the background, you don't necessarily need to worry about that so much. I think it's still important to know the data types. It's important to know that there's a difference between ranked data and quantitative data. There's a difference between data that has a true 0 and data that doesn't have a true 0. How those numbers interact really does change based on kind of the underlying structure of the data. And yet, when you want to sort of predict A from B, there are methods of predicting categories from quantities, which is what we're doing right now. Do you need to know that it's called linear discriminant analysis? I don't know, maybe not. But we're going to use that term today. But just keep in mind, a lot of this stuff is sort of interconnected. So this is an example of linear discriminant analysis. Essentially, we've got these 2 different categories, in this case, red dots and blue dots. We want to try to, essentially the goal of LDA is to draw a line between them, a straight line between them. And actually it can get a little bit more complicated than that, but we're just going to assume it has to be a straight line for now. And another way of saying this is what we want to do is define the group mean center. So if I said, what's the center of the blue dots? I could do that. I could pick a spot that I think is sort of the center of gravity of all of those points. And that's what the stars are in these examples. Apart from the stars then, the neighborhoods between them, described as sort of blue and red polygons. Essentially what you're looking at here is the nearest neighbor of those. So at what point what point is closest to the red star center? Which points are closest to the blue star center? So we're not really, this is exactly the same as sort of a Voronoi or Thiessen polygon approach. Once we figure out the group mean, then the line between them just sort of becomes the corresponding Voronoi polygon boundary. So one of the things that I kind of hope you're picking up on is the interrelationship between a lot of these approaches and how flexibly you can approach your data analysis. You can sort of use some of these approaches to approximate the solutions in another kind of an approach. So one of the things that you can yield out of this as well is sort of essentially the equation of a line that would describe that boundary. To do this, we are going to use a package called scikit-learn. So scikit-learn is kind of a core component of the scientific Python community. You can use it for all kinds of things, and it's increasingly being integrated into ArcGIS via the ArcGIS Learn module, which is sort of built on top of a lot of these things. So we're only going to be able to talk about a couple of different things, but this is a really powerful package. If you find yourself kind of getting more into data mining, data analysis, I would encourage you to keep giving a look to scikit-learn. There's just quite a bit of material in here that you can focus in on. Okay, so I'm going to show you some of this stuff. Basically, we've got sort of standard import statements up at the top, but under classifiers, I'm bringing in things from scikit-learn. So when you see these names, k-means, PCA, random forest classifier, all of these are being brought in from those respective packages. So this is what a simple LDA analysis would look like. One of the things I want you to focus on here before we look at the results is just look at the code and appreciate for a moment how little code it takes to do this. So used correctly, all of these different packages actually have a very similar kind of a run profile. They look very similar, and they're executed with very little code. And as you're working with the stuff, maybe you're working with it separately in Anaconda, or you're trying to do the stuff within an ArcGIS notebook. Remember that what we're looking at here are generally pandas data frames, right? And we've talked about many times that all of our vector data that we bring in to ArcGIS Pro can essentially be very, very easily converted with one line of code to a spatially enabled data frame. And I would encourage you to start working, keep working and start working within that framework. Working with these things as pandas data frames is just sort of the lingua franca of data science. Don't worry so much about the old school ways of processing this data. Try to do all of your work within this kind of pandas umbrella. Okay, so what about the specific linear discriminant analysis? Well, the very first thing that we do is we're creating an LDA object. So we take and we invoke that linear discriminant analysis that doesn't take any arguments, and we get back this LDA object. And then all we are doing here is we're extracting the columns that we want. So from our entire iris data frame, we're just extracting petal width and petal length. We're calling our Y data species, right? That's the data that we want to predict. Those are our classifiers in effect. And we are fitting the data. So we take the LDA object, we call a fit method on it, we give it our X data, which is a data frame with a couple of columns. We give it our Y data, which is a pandas series object, essentially a one column data frame, and we get our results, and that's all it takes, right? So one line of code effectively does all of this work, and then we can print those out. What we're printing out here, so this is an object that has a number of different statistics in it if you're interested. All I'm pulling out right now is the means. So those means are the mean cluster centers, right? So how, you can kind of eyeball this. How good of a job did it do? Pretty well, right? We took our categories, we tried to guess the centers, we put X's down where those centers were, and then the next thing that we can do is we can try to predict class membership based on those X's. When we do that, we call this thing, so we say LDA.predict. we try to guess what those what categories those should be. So in other words, the first time we ran this, we found where all of the setoses were. We essentially, and this is essentially all we did, we took their average on petal length, we took their average on petal width, and we said that's the center of that category, right? A very intuitive approach. We did the same thing for versicolor, we did the same thing for virginica, and when we do that, we can then go back on a second round and say, based on these mean centers, if I didn't know what category they were in, where would I put them? And so if you look at that scatter plot, you would sort of put them to whichever X is the closest. And that's essentially what goes on here. So we say LDA.predict X, we get our predictions out, and then we can compare how well we did versus the truth, so df.species, versus what we guessed, which is our predictions. And we can print that out in what's called a confusion matrix. So that's what we're printing out here, and that's what you see down below is a confusion matrix kind of at the very top here. So this is our confusion matrix. And then we're also printing out a classification report. So we want to know how well we did with this stuff. And we're going to print these things out. Our percentages here are given in precision and recall and an F1 score. Our support is just the number of observations that we had. And then we're also printing out Cohen's kappa, which is a score. Now we're going to talk about what all of these mean here next. So how good of a job did we do in predicting these categories? Just from our confusion matrix, we guessed, so I think these are going probably alphabetical order, so Setosa, versicolor, and virginica. We had 50 setosas, and we found 50 setosas, right? We classified none of them. We didn't classify any setosas mistakenly as virginica or versicolors, nor did we accidentally categorize versicolors or virginicas as setosas, right? So we didn't make any mistakes on this category. We did make a couple of mistakes with the other ones. So we captured 48 total of the 50 versicolors and 45 total of the virginicas, with a couple of misclassifications on each of those. So when we look at the confusion matrix, we can see what's been misclassified as what. Oftentimes, though, we'd really like to say how good of a job did we did on average with this whole classification process. So we're isolating these things out. Here's our confusion matrix, also known sometimes as a cross-tabulation matrix. Let's talk a little bit about a concrete example. So suppose we're writing a computer program whose job it is to be shown a photo and to say, is this a cat? Sorry, is this a dog? And I'm going to use the expression here, is this a cat? What I really mean here are not dogs, right? So all we're really saying is this a dog or is this not a dog? And I happen to give it some pictures of cats. Maybe I should revise this example to have other things in there for clarity. So is this a picture of a dog? I showed the computer program, I give the computer program 17 different images, and it finds 8 dogs, and it says these are dogs. So all the things that it thinks are dogs are shown in the circles. So up here's a dog, and that's a dog. Wait a minute, that's a dog, and that's a dog. You can see that it's made some mistakes, right? We found 5 different things that are dogs. Those are given in the green circles. But we've also decided that these 3 other things in circles are also dogs, when in fact those are cats. So the correct responses for dogs are shown in green circles, and some of the mistakes, the mislabeled dogs, are in red circles. We also made mistakes in a couple of other ways, because we said, let me get a different color pen here. We said that that was not a dog. We said that this was not a dog. We said that this was not a dog. Those are definitely dogs. And so we've made mistakes in a couple of directions. We've classified cats as dogs in 3 cases, and we've got 1, 2, 3, 4, 5, 6 cases where, let's see here, add that up right, 1, 2, 3, 4, 5, 6, 7 cases. There we go. That adds up to 12. 7 cases where we were shown a picture of dog and we said it was not a dog. Now the easiest statistic to calculate is just the total accuracy. How many things did we get right divided by how many things did we get wrong? How many things did we get right? One thing we got right is these 5 green circled pictures of dogs, right? They are dogs. We said they were dogs. We get credit for those. We also were shown a couple of pictures of cats that we decided were not dogs. We've got two pictures of cats here. Here's one and here's one. We've got a couple of cats that we were also right about. So 5 dogs and 2 cats we were correct about. That's 7 out of 17. So we were 41% accurate. And then total error is just the complement of that. So we were 59% error rate. So that's a pretty bad classifier. We didn't do so hot. But data scientists use a couple of other words to describe this. So we might express these ideas in terms of what's known as precision and recall. So precision, we would say we were 5 out of 8 precise, and our recall score is 5 out of 12. And we'll talk about what those mean right now. So let's break this down into a couple of things, a couple of key numbers to calculate precision and recall. How many dogs did you find? I found 5 dogs. Those are the green circled dogs. How many things did you think were dogs? Well, you told me 8 things were dogs, including these 3 cats. How many dogs should I have found? How many dog pictures did I show you? I actually showed you 12 dogs. So out of the 12 images that I showed you, you correctly identify, or out of the 17 images that I showed you, 12 of which had real dogs, you found me 5 dogs. But you thought 8 things were dogs. And these are essentially the things that are going to matter for determining precision and recall. So precision and recall looks something like this. This is for our Setosa data set. We are measuring, the precision is essentially the true positive rate. So it's the true positive divided by the true positive plus the false positives. And recall is the true positive divided by the true positive plus the false negatives. So it's 2 slightly different views on this. And these are the results that we got for our linear discriminant analysis. Setosa had a precision of 1 and recall of 1. We actually scored perfectly with respect to Setosa. So that's the first column. Versicolor, our precision score was 91 and our recall was 96. Virginia was, well, I think that's supposed to be Virginica. Anyway, precision is 96% and recall is 90%. So we're still not done getting into this. If this doesn't make total sense yet, not a problem. We're still in it. So let's bring this back to our dogs. How many dogs did you find? I found 5. How many things did you think were dogs? 8, right? True positive is 5. False positive is those 3 cats that I accidentally said were dogs. So true positive 5 divided by 5 plus 3. So precision is 5 out of 8. The recall looks like this. It's the same true positive, so that's still the 5. But now the denominator is the true positive rate. Is the true positive, so that's 5 also. But how many false negatives, right? How many dogs did I miss? I missed a few, right? How many total, another way to put this is, how many total things were dogs? How many things should you have found that were dogs? And that's 12. So I actually told you there were 5 dogs. I should have found 12 dogs. And then we like to combine those 2 things. So these 2, precision and recall, define 2 different metrics of what it means to be right. Sort of how well we did versus the number of dogs that we should have found. So that's recall versus how many mistakes did we make about things we called dogs but were actually cats, and that's precision. So two different dimensions of accuracy. And we combine those into a thing called an F1 score. And the F1 score formula is given up here, but it's essentially just the harmonic mean of these. So it's always going to be essentially a weighted average of these two numbers. And loosely average, right? So a harmonic mean is a kind of a mean. And when I say weighted, I mean that the support or the number of cases that you had is going to be used to weight this. And that's really important for reasons that we'll talk about here in a second. So it's essentially a kind of a weighted average. The last thing that you're going to get here that I provided here is a number called Cohen's kappa. Now there's some disagreement within remote sensing about the value of Cohen's kappa, but it's still widely used. It's not all of these sort of single number metrics of agreement or accuracy have their problems because accuracy can be sort of a multi-dimensional thing. It's sometimes hard to just put a number on a thing. How good was that movie? Well, I liked this part of the movie, but I didn't like that part of the movie. The pacing was good, but the sets were terrible. The acting was terrible, but the direction was amazing. The story was good. So sometimes it can be difficult. Sometimes those things all hang together, and sometimes they don't hang together. And so sometimes when we try to report a single number for accuracy, or let's call it quality of fit, quality of prediction, we sometimes fall down because we can't always compress this multi-dimensional space into smaller dimensions. Anyway, that's a long way of saying we do have this way of describing a single number of accuracy, and that's called Cohen's kappa, and that's down here. So just like the R squared value tells you sort of, or the R, actually this is a little bit more related to the R value. Just like an R value tells you the degree of correlation between two quantitative variables, Cohen's kappa tells you the correlation between the right answer and what you guessed. It was actually designed in psychology to measure inter-rater agreement, where there isn't necessarily any accuracy at all. We're just sort of measuring the judgments of people and how well they correspond. So it's essentially a measure of correlation, but used in remote sensing and machine learning to rate the quality of a fit. So in this case, our Cohen's kappa score was, let's call it 0.93, 93% accurate. So our LDA, our linear discriminant analysis, we talked about sort of how it was done, and that was pretty easy, right? We just sort of find the group means. We make a categorization based on the, which of those group means you're closest to, and then and then these are all metrics of sort of saying what the accuracy is. So we say our LDA had a total accuracy score of 93%. When we talked about regression, which is again essentially what we're doing here, we're trying to predict categorical variables off of quantitative variables, but it's still prediction, still sort of statistically based, so it's still basically a kind of regression. One of the things that we said is you can add variables to a regression to make it more accurate, right? If I am trying to predict the election results, maybe I want to take the average population density of the county, but maybe I also want to take the median income, and maybe also I want to take the education level, and maybe also I want to take 5 other things and try to predict how that election is going to swing out. I can do the same thing here. So far, we looked at one scatter plot, and we were basically using that to predict our class categories. I showed you what the third dimension looks like and how you can look at that. What if we wanted to use all of our 4 columns? So sepal length and width plus petal length and width, so 4 different variables to try to predict our predict this class membership. Just as before, we will always add value with every additional variable. How much value we add may be infinitesimal, but always positive, but could be infinitesimal, or we could add a lot of explanation. In this case, we we went from a two column model to predict, and we were at 93%. We added 4 columns, and now we're up to 96%, assuming we think of Cohen's kappa as a percentage. You can see that things have gotten better kind of across the board with respect to precision and recall. So Setosa is still perfect, but we boosted our numbers a little bit for Virginica and Versicolor. We're now getting 48 right out of the 50 for each of those, and confusing only 4 cases between them. So this gets to be sort of a bit of a crux in data analysis. We can always add more data to get a better fit. So now we're using 4 variables. We boosted our accuracy. Is that what we want to do? This is a judgment call. Sometimes science is more art than science. You've got to figure out whether that is actually warranted or not. If all you want to do is predict your data, then sure, that's fine. But if what you want to try to do is sort of explain how these things work, you usually want to keep things simple. You want to keep your model parsimonious. You want to have the fewest number of variables that adequately explain what you're trying to explain. Einstein had a saying, everything should be made as simple as possible, but not simpler. And that's essentially what you're trying to do with this. You want to add columns, you want to add explanatory variables in as much as it helps you explain what's going on or investigate the relationship between variables, but you don't want to go further than that. So we've sort of quickly beelined into Cohen's kappa and F1 scores and precision and recall, and probably all of those things are unfamiliar to most of you. Why can't we just use total accuracy? Why can't we just say what that percentage is? That seems like that would work. And let me give you an example of why that doesn't work. Let's say I've got a raster and I want to try to predict which pixels in my raster are impervious surface. Think in your mind of what a satellite photo looks like. Maybe it's multiband, maybe it's just RGB. I've got an image of a place and I want to predict which of those pixels are impervious surface. In almost any non-super urbanized area, if you take Blacksburg for instance, most of those pixels are not going to be impervious, right? There's only so many roads and houses and sidewalks that we have. Most of what we have is still green space, right? Not everywhere, not downtown, but over the course of the whole city, probably, we could maybe guess that 1% of our pixels are impervious, just as a ballpark. If I'm trying to write an algorithm to pick out which of my pixels are impervious and represent an impervious surface and which ones don't, I could write a really stupid algorithm that all it would say is everything is not impervious, and my classifier would be 99% accurate. Is that good? Not at all, right? We are completely missing the point of what we wanted to do. We wanted to tell the difference between which pixels are what. And if all my classifier ever does is just say, nope, not impervious, nope, not impervious, and yet that's true 99% of the time because my underlying phenomena is only present in 1% of cases, I don't want to count that as a good model. I don't want to count that as a good algorithm, right? So this is where precision and recall really help us discriminate in a way that total accuracy does not. So I would encourage you to stop thinking with respect to all of these kinds of things, thinking about them in terms of total accuracy, and start thinking about them in precision and recall and F1 and Cohen's kappa, and maybe some others. But if you can think of these things, if at least you've got a good conception of why I don't want to use total accuracy, you're going to be in good shape. So let's go on ahead. As an example here, this is a fun image I kind of came across last year. A chart to help determine risk of bear attack. This is a terrible model of bear attack risk, and yet it's probably from a certain point of view, it's 99% accurate. It's just not very specific. A similar example would be if you wanted to know what the forecast is tomorrow, and I told you that it's going to be at least negative 100 degrees Fahrenheit. That statement is 100% true. I will be right all the time, but what I'm not is very specific. And so models have to be not only accurate, but they also have to be specific to what you're doing. So another approach to classifying things is k-means clustering. This is probably one of the most powerful and yet simple techniques that exists. It's really strongly related to the linear discriminant analysis, and so hopefully you're going to find this to be a powerful approach. And we'll talk about how this applies to geographic data here in a second. So LDA works when we already know the classes. So if you think about what we did to do an LDA, we essentially found all of the setosas. We figured out what the mean petal width was, and the mean petal length, and the mean sepal width, and the mean sepal length. And we figured out what the mean was. And all we did was sort of figure out, we sort of imagined a space where those are our sort of x and y coordinates. And whatever one we're closest to, whatever class mean we're closest to, that's what we use to decide which one we go in. But a lot of times we don't know what classes these should go in, right? When we have a regression, we can do that. We're sort of running an analysis based on the data that we have. And it's not to say that we can't predict off of that, because we totally could, right? We could take our samples of Setosa and Virginica and Versicolor. We take our sample and we figure out, what the average mean is for Virginica. We can apply that to new data, so that's not a problem. But it does presuppose that we've already classified things. So what do we do if we don't have that information? That's where k-means clustering comes in. The gist of this is essentially, given the scatter plot that you see here, we want to. So imagine we don't know how these break up into categories, right? As a human, you're looking at sort of the initial scatter plot. Try to ignore the symbols here for a second. I know that this is kind of on repeat here, but pretend those are just symbols. How would you define the classes for these clusters? That's essentially the goal. So the way that k-means clustering does, the k just says how many clusters do you want me to find. So the algorithm is kind of a dumb algorithm in the sense that it doesn't start with a knowledge of it doesn't sort of fit itself to the data for the number of categories. You have to tell it how many categories you think there are. And then from there, what it does is it essentially plunks down some points, right? So these are given by the class mean centers again. In this case, the black crosses. Those are sort of the estimates of the centers. And then the computer starts moving it around. So the computer essentially calculates what went in there, what the accuracy was, and then, or what the variance, not the accuracy, because we don't know what the true ones are, but the variance in here. And we just start moving those class centers around to try to minimize the variance. So it's kind of a goodness of fit criterion. So this makes it an iterative method that makes it somewhat computationally expensive. And it's also a little bit sensitive to what those initial guesses were. So what I said happened was we essentially take 3 crosses and we just sort of drop them on the map. Where they drop is going to be a little important to what the final solution is. Sometimes the problem that you're working on is not that sensitive to the initial guess, and sometimes it is. But you don't necessarily know that unless you vary the initial guesses as well, which you can do. There are other extensions to k-means, so there's k-medians as well, so that's the sort of non-parametric version of this. But k-means is kind of the standard. So this is another view of this. This comes from the Wikipedia page, I'm pretty sure, on k-means clustering. So given our data, which is given here in the gray squares, we make an initial guess, which is sort of random. We're trying to guess three things. So K is 3. We put a red dot and a blue dot and a green dot, and those are going to be the centers of our classes. So the next thing that we do is exactly what we do in the other case. We basically build neighborhoods based on which dot that box is closest to. And so the neighborhoods that we come up with look something like what we see here in panel 2. And then when we do that, what we do is we compute the sort of dispersion in our categories, and we're trying to minimize the dispersion within a category, maximizing the dispersion between categories. So we just sort of tweak these things around a little bit. We move the centers around, we rerun the analysis, and we sort of see how that dispersion works. And as we move these class boundaries around a little bit, we start to sort of converge on a solution over time. That may take 100 times, that may take 1,000 times, but we just sort of let the computer run until we stop observing a lot of. We can either say we want it to run for a certain number of times, or we can say, well, if this new solution doesn't differ from the last solution by a certain amount, that's when we stop. To run a k-means clustering on data is very, very easy. So just like we saw with LDA, linear discriminant analysis, we essentially just create a k. This time actually we're combining these, and we could have done that, but note the syntax here. We're creating a k-means object, and then we're immediately fitting it. So we're sort of doing this all in one swoop. So we create the object, we tell it we're looking for 3 clusters. There's a random state initialization that we can control if we want to. And then we fit our data. So our data is just the petal width and the petal length. And you'll notice that one of the things we're not giving it, we can't give it because we're sort of pretending that we don't know, is the species, right? So we don't know what that species should be. So we run our data and we print out the results of that. We get our cluster centers just like we got with linear discriminant analysis. So the grid here, the array that we're looking at, are the x and y variables here. So that's x and that's the y coordinate of these class centers, and we print them out. And we can see that actually so let's see, we're printing out the k-means here in triangles. We have a previous run of our LDA that we can compare to. So those are the black X's, and sure enough, the triangles are what we guessed when we didn't know what the categories were, and the X's are the class centers that we had when we did know what they were. How good of a job did we do? We actually did really well. And if you run the numbers, you will find that we actually did better with k-means clustering than we did with LDA. So these are the official numbers coming out. So the confusion matrix, we found the setosas were all easily found, right? Those are relatively well segregated in the scatter plot, so it's not too surprising that the computer did a good job. For Virginica and Versicolor, we correctly predicted 46 out of those with just these 2 columns, and we mistakenly we misallocated 4 of them either way for Virginica and Versicolor. So the results here, you can see the precision, recall, and F1s for those individual values, and then Cohen's kappa for this whole thing ended up at 0.92. One of the things that I hope that some of you have thought about is whether or like all of this seems really familiar. And in fact, the way that natural breaks works, I think for the people that may be in the geovisualization class, they may have seen a little bit on this with respect to goodness of fit. But the natural breaks algorithm within ArcGIS Pro is essentially a k-means clustering algorithm. It's really just trying to figure out where these class boundaries should be. Another way of putting that is what the class centers should be based on the data inputs and spitting those out. And of course, you have to give it the number of classes, and based on the number of classes that you give it, it figures out these class boundaries again to minimize each the deviation within each class and to maximize the deviation outside of each class. Our good friend George Jenks strikes again. Within ArcGIS, there's a tool that does this stuff for you now. This is the Find Point Clusters tool. Also, kind of awesomely, it will try to detect noise. So instead of trying to fit each thing, it also tries to fit noise to the data. So there are tools to do this in Arc now. The examples. I'm not going to provide you with a geographical example in this particular case, but you could imagine sort of taking the Baltimore 911 data or something like that and trying to break it out into different clusters. Okay, so we've talked a little bit about taking quantitative metrics and predicting a category. So linear discriminant analysis and k-means clustering essentially try to partition things into groups. What we're going to try to do now is talk a little bit about another way of thinking about that that's a little bit more flexible. So this is called principal component analysis, and it's essentially a dimension reduction technique. In some ways, what we're going to see here are ways of sort of creating what effectively are indices, groupings of quantitative variables into another quantitative variable that represents a kind of a thing. So we're not predicting categories per se. What we're really trying to do is we're trying to figure out what kind of variables hang together to form clusters of quantities. We'll see a couple of examples of this, and this will probably make more sense as we go. One of the things that as we see is that as the set of attributes gets large, the space becomes very sparse. So if you think about what we've looked at so far, which is scatter plots, right? When we have a scatter plot with 2 dimensions, those dots tend to hang together pretty easily. It's not too hard to see clusters on a scatter plot with 2 dimensions. When we start to add a 3rd dimension or a 4th dimension, things kind of cluster together, but as you get into 50 different axes or 100 different axes, the space just necessarily gets really, really large in between them. So this is sometimes known as the curse of dimensionality. Again, what we're really after here is to try to come up with how different quantitative variables hang together due to some underlying factor or explanation. And we're going to be talking about PCA, but the relationship to factor analysis is actually pretty strong. We're not going to get into that too much, but it's not that much different than what we are talking about. So the idea here is maybe we think there are certain kind of latent abilities in the way that humans kind of solve problems, right? Some people are better at math, some people are better at verbal stuff, some people have higher spatial ability. We think that these things work together. Another way of thinking about this would be types or genres of music or movies. We might think that there are ways of sort of getting at different scores, like batting average, that might represent your offensive capability in baseball. We're trying to find numbers that are going to sort of represent a big axis of what we're trying to do. This really, part of what we're doing here separates the difference between what we can measure and what we want to try to capture, what we want to try to represent. So if offensive capability in baseball is what we want, batting average is a measurable quantity that we can use to assess that. If we're trying to figure out which people are going to be the best pilots, we want to give them tests, things that we can measure that we think represent piloting ability. And maybe that itself has different components. So a lot of what we're trying to do here is to take a lot of different sort of actionable, measurable, specific tests or parameters and group those together into something that we think represents kind of a main idea. within the sphere of human geography or world geography, indices like the Human Development Index try to combine individual metrics that correspond to life expectancy and education level and per capita income to try to combine all of those together to form like how good it is to be in that country, right? How well off is your population? So it's not just money, but life expectancy, which represents health, and education, which represents sort of human achievement. All of those things together are form this one factor of what it is to be healthy and happy within a country. Similarly, different factors might combine together to form something like what's the corruption level within a country. So there are lots of different kinds of indices that you can make, but that's essentially the central idea. We take multiple different directly measurable quantities, and we combine them together in some way to form a factor. If we do this with a big pile of things, we can sort of separate out these things kind of fall together in this factor, and those things fall together in that factor. So what does that look like? Basically what we're trying to do is on 2 dimensions, we could think of it this way. We gather our data in 2 columns, we plot them out, and essentially we try to find explanations for our variables that describe most of the variability. So in this case, we plotted our data out. What we try to do is we try to find orthogonal axes that help discriminate between our things. And in this case, we would fit a first axis kind of along the long dimension here that would sort of partially describe our data. And then the second dimension would be sort of the 90 degrees to that. And all of our data essentially varies according to these dimensions. What we're really trying to do here is to try to factor out the intercorrelation between our data, right? So if human income, median income, and life expectancy are correlated, and they are, what we want to do is try to rotate out that correlation to really find sort of axes that describe what we're doing, and sort of in this sense, maybe if you imagined that this data, and it didn't come from there, but if you imagined that this data was income and life expectancy, and it looked something like this, what you would find is that sort of the first dimension would be something like rich and healthy, and then the second dimension would be something else, and that helps us get at what this second dimension is, and captures the variability along that axis, and we would have to look carefully and sort of see what we think, how we think those things relate. So in our PCA, we would start with something like this. We have our scatter plot. What we want to try to do is say how do we describe these things? We're not trying to guess categories anymore. So even though these things are colored, try to put that out of your mind. We're not trying to guess the category. What we're trying to do is say, like, on what axis do these things really change? To do that, essentially what we want to do is we want to combine these things together. This would be like taking an average of petal width and petal length and sepal width and sepal length, and using that to guess what's what. What we actually do, though, is we transform these things into z-scores. So if you noticed on the last slide, those are kind of 2 dimensions that look the same. And of course, the things that we measure are almost never the same, right? Petal length is going to be really different than petal width. And so how do we put those things together? We use a z-score, right? We do this standard transformation so that we've got a quantity that we can directly compare. So that z-score is an incredibly powerful transformation, and it's something that you should be very familiar with. We also know that if we're going to try to find dimensions, different dimensions don't necessarily contribute equally. So sometimes things are stronger determinants than others. And so one axis, one factor may explain more of the variance than the other factor. And in the scatter plot here, if we drew that kind of axis running southwest to northeast along our plot, that would be the principal component. And then the second dimension would be orthogonal to that. And that second dimension would not be nearly as valuable as the first one, because there's less variability generally along that axis. And that's pretty normal, right? We don't think that all of our things sort of contribute equally. Different inputs will have different sort of weights in the back end, sometimes a lot, sometimes a little. PCA is pretty fast, this is the math behind it is less iterative and more, let's call it statistical, and for that reason, the numbers that come out of PCA come out pretty fast. You can actually analyze pretty big data with PCA on a standard laptop these days. So we could use PCA to investigate sort of how these four different things hang together. So petal width, petal length, sepal length. How do these four input variables kind of compress into two different dimensions, right? Petal width and petal length are strongly correlated, and they kind of might form a, like, petal size would be maybe that axis. Why would we use two components? First of all, two components is pretty common, partially because that lets humans look at it. We often decompose PCAs into two dimensions. Even if we're going to divide them up, we might have 60 columns worth of input data. We'll often still compress that into two dimensions just to look at it, if nothing else. One of the things about PCA is it's actually pretty flexible in terms of how many dimensions you want to look at. So this line here, if we don't know how many components we want, we can instead say, I don't care how many components there are, but I need you to explain at least 90% of the variance. So instead of k-means, where we have to decide how many categories, we can say we want two dimensions, or we can say, you tell me how many dimensions there are by looking at the data. But then you have to say, what quality of fit are you looking for? So this is a PCA transformed space. So what we've done again is we're trying to compress those four variables into two variables, right? So already you can maybe take a hint at what those might be, right? Because we've got petal width and length and sepal width and length. So maybe these things essentially boil down to petal size and sepal size might be a better way to put it, right? So that's what PCA lets us do. It lets us combine these things into a smaller set of variable. Once we do that, we can then feed essentially those results into a classifier like we've seen. And the question is, as a human, you could ask yourself, are these clusters more visually distinct than what we looked at before? And sometimes they will be, and sometimes they won't be. So running, I'll tell you, running these things with all four variables intact is again the easiest way to achieve higher accuracy. But if that's not what you're looking for, if you're looking to kind of to break these down into more approachable, understandable things, sepal size and petal size in this case, then PCA is the kind of thing that will do that for you. So don't always be thinking in terms of maximizing your explanatory ability, right? That's not always the game. Sometimes the game is understanding how the system works, and that's where PCA comes in handy. All right, so one of the really hot topics in terms of predicting classifiers, predicting categorizing classifiers is random forest classification. This has gotten to be really big, partly because it doesn't require a statistical decision. We're deciding things based on equations of lines. What we're trying to do is we're trying to come up with a way, often the same way that human beings would do this as they try to classify things. So as an example, I took a forest ecology class many years ago, and part of the task was to be given sort of a small little clipping from a tree, a little bit of a branch and some leaves, and based on what you see there, can you figure out what tree that came from? And you look at things like, what is the leaf shape like? Are the edges smooth or kind of jagged? Does it kind of have a lobe structure or not? Are they shiny or are they smooth? Lots of, are there this many buds or do the buds look like that? Right? All of these little kind of measurable indicators are combined, and you kind of, you kind of follow down the taxonomy and you say, well, it's got this many leaves and are they alternate or are they pinnate? Oh, they're pinnate, and so you kind of go down a different thing. Those things are called decision trees. So a decision tree is what guides you to figure out what it is what that particular tree is typed as. Many of you have probably had an experience like this in your science class. This is a decision tree for whether or not you want to play tennis. So the first thing you might want to do, other than looking to see if you want to play tennis or not, which might be a good first question, is what's the weather like? So if you look outside, you can decide, well, is it sunny or is it overcast or is it rainy? If it's overcast, then you say, yep, that's the perfect day to play tennis. You go outside. If it's sunny, then you have to ask yourself, well, is it really humid out? Because I don't like to play tennis when it's really humid out. So if it is humid, then I'm not going to play tennis. And if it's pretty good, then I'll play. If it's rainy out, then you might ask, is it windy? And if the wind is not too strong, you might decide to play tennis anyway. I probably wouldn't, but you might. Other things you might have in here: the temperature, like you said, whether you wanted to play tennis, is your friend available to play tennis? All of this stuff might also go into the decision tree. Random forest is essentially a collection of these decision trees. What we do is we segment out part of our data. So we have our pile of data. We want to figure out what's a Virginica, what's a Setosa. What we do is we say, well, we're gonna take this percentage of our data, randomly select 80% of our flowers, 80% of our plants, and we're gonna make a decision tree out of those. But then we're gonna throw those back in the pile, and we're gonna again randomly draw another 80%. Right? Some of those will be the same, some of those will be different. We construct a decision tree, and as we do that multiple times, we get these sort of multiple perspectives on what the decision tree should look like. Why don't we just run our decision tree on all of the data? We can, but if we do that, then we're likely to get what's called overfitting. So peculiarities in our data set are going to start to dominate and try to help us make decisions spuriously. And so what we found is that it's better to use the sort of probabilistic multiple random samples combined together than it is to just sort of use your whole model and then use that to predict. It prevents a lot of sort of, I call it like squirrely behavior when you get into the weeds of particular little random values in there. So to avoid overfitting, we instead model this multiple times randomly, not unlike a Monte Carlo simulation. So as a human, you can look at these two scatter plots and you can say, if you had to decide based on these two scatter plots, what is a Setosa, what is a Virginica, what is a versicolor, could you do it? You could pretty easily say, well, like Setosa is pretty easy. If your petal length is below 22 and your petal width is below 8, then you are a Setosa. So that could be sort of the first couple rungs in your decision tree. Things will get trickier as you get into this space. And so as you kind of try to construct these trees, you'll use all of this available information to help you figure out how you kind of create this diagram that sort of says, if greater than this, if less than that, if these two together are this, then it's this kind of a plan. The way that this is done is pretty easy. So again, this is the random forest classifier inside scikit-learn. Again, a lot of the new ArcGIS Learn module stuff is kind of based on this. It kind of wraps around scikit-learn. So all we're doing here is we're giving it our X data, which is all of our prediction columns. We're taking our species data as our thing to be predicted, and then we're fitting our data. So this looks exactly like the two classifiers that we've seen before, k-means and linear discriminant analysis. And we get exactly the same thing. We predict our results, we generate a confusion matrix, we get a report, we calculate a kappa. And the results look like this. Again, Setosa was the easy one, right? Even visually as a human, you can see the difference between these two things. It's not at all hard to pick those out. How well do we do on the other ones? We did okay. We've actually made one more error than the last thing that we looked at. So we got 45 of the versicolors right and 46 of the virginicas right. But we've now made 9 classification errors. The accuracy, Cohen's kappa, 91%. So it's not great. It's also a little bit slower. If you try to run this stuff, you're going to find that it runs a little bit more slowly. And again, the total accuracy was not better. Why would you use this if the accuracy isn't better and it's slower? Well, part of the reason is that it doesn't assume normality. So we've described a little bit sometimes when our data is not normal, when it's noisy, when it's kind of clustered in really kind of weird ways. Sometimes a lot of the statistical approaches don't work as well. So the linear discrimination analysis and k-means clustering are going to work fine in many, many cases. Those are venerable, great statistical approaches that make a lot of intuitive sense and do a good job predicting most of these things. And yet they start to fail when your data gets weird. That said, your data might be weird or it might not be weird, and this is why you need to plot it and look at it and familiarize yourself with it. But I would caution you, this is why you don't just reach for the newest, shiniest thing. Random forest classification is good. It's useful. I hope you do use it. But is it going to produce better results than essentially regression? Sometimes yes, sometimes no. One of the things that k-means clustering tends to do is it tends to overfit your data. So we talked about this briefly a couple of slides ago. Let's talk about it a little bit more now. So when we say we're creating decision trees, what we want to do is say if petal width is less than this, and if petal length is less than that, then you are a Setosa. And that works great, right? And what we've seen is all of these things find the Setosa cluster very easily. All of these things have trouble finding the boundary here, right? Between Virginica and versicolor. And if you try to construct a decision tree that tries to separate these things, it starts to look like you see this. If petal width is less than 16, you're versicolor, unless the petal length is above 52, but less than 54. If your petal length is greater than 16, then you're versicolor, as long as your petal length is between 40 and 54, and the petal width is at exactly 42, right? That is a terrible decision tree. That is not what we want these things to look like. And yet, this is essentially what your computer does in the background to try to figure these things out. And this is why you have to run a lot of these in a random forest, and you can't just trust it to make a decision tree. It doesn't always make the kinds of choices that we would like it to make. So combating overfitting is really important. It's probably one of the most pernicious issues in machine learning, in data science. The models that we make absolutely need to be run multiple times. We need a lot of simulations. We need to make sure that we're dividing things up into a training set and a validation set. We need to do a good job of being on our guard about overfitting our data. because machine learning is going to tend to try to make things that look like the green line to figure out what's what. And that's not really what we want it to do. What we want it to do is something like the black line, where we're sort of dividing up between a nice smooth categorization, and we're chalking the rest up to noise. And we're not essentially modeling that noise as a real phenomenon. By convention, what we tend to do is we take our big data set and we split it into an 80-20 pile. We use 80% to turn the data, and we use 20% to validate it, which means we take 20% of our data set out, we don't look at it, we run a random forest classifier, and then we use the 20% to find the accuracy. And then you can do that multiple times, again, as we've talked about, to get an idea of the variance of the result. There are a lot of really good examples of overfitting. So if you're interested in this, it's kind of a favorite topic. Again, it's super common. And you'll see these things happen all over the place. When Nate Silver talks about pundits, or if you listen to, you're watching sports and you hear some of these statistics, you've probably heard things that are like this. So this is a really good XKCD cartoon talking about overfitting in the context of presidential elections. And you can read through all of these at your leisure. They're a lot of fun. 1984, no left-handed president has ever been re-elected. No one with two middle names has become president. No Democrat has won without a majority of the Catholic vote, and so on and so on and so on. All of these things are true until they're not. So which technique should you use? This may surprise you, but I guess my take on this is in a lot of cases it doesn't matter. I would encourage you to try to keep things as simple as you can. Use a thing that does a job that's the most familiar to you and that you understand. If you get used to using linear discriminant analysis, that's going to work well for many, many things. When will that start to fall down? It'll start to fall down when your data is not normal. If you have a lot of outliers, if there's a lot of noise in it. Well-behaved classes are always going to be detectable. So Setosa, in our examples that we've looked at so far, was always really easy to find. It was the other two classes that were harder. And there's no magic solution here. So this is why I kind of say that it doesn't make a heck of a lot of difference. Some things that I think you should pay attention to. One is efficiency. So be mindful of whether these approaches run quickly. It may run quickly enough for your test data set, but be aware of issues of scale. So if your code, if your algorithm if your process of analysis works fine for 100 items, but starts to not work very well for 1,000 or 10,000, that's a scaling problem, and your approach is not scalable. Some of these techniques will start to bog down with very large data sets. Probably not with anything that you're likely to work with, but you never know. You should know the difference between precision and recall, and especially why you shouldn't just use total accuracy as an assessment metric. If anybody ever says, "Oh, what's the my algorithm was 98% accurate," you need to dig into that, and you need to know how many cases there were and how they measured that. That stuff gets obfuscated all the time. You need to know a little bit about outlier handling. How clean does your data need to be to get good results? Cleaning data, as we've talked about all term, is an important part of it. But hopefully your approach is able to handle a little bit of noise without totally breaking. PCA can work just fine with medians rather than means. So you can make some very minor modifications to some of these techniques to make them work well. And then validate. Never just trust that your classifier worked perfectly. Dig into the quantitative reports. Look at a couple of cases to see how they sorted out. Sort your table and kind of eyeball it and see if the results make sense. Never just blindly trust the results of the reports that you're getting back. I'm not a big I don't think it's super necessary to understand all of the mechanics. The more you understand, the better. But we all have content that we're trying to master and other things. And so we can't all be experts in the math behind random forest classification. And I would say that you don't need to be. You need to understand enough about how it works to understand why it would fail, where it works, where it doesn't work, why you would want to use it over a different tool. So I think a big part of that is just experimenting with the data. We'll be providing, and we'll talk about here in a second, a data set that you can play around with to sort of test out some ideas on this front. K-means clustering is probably the strongest technique in this realm that you have not heard of. It's simple, it's reliable, it's intuitive, it runs pretty well. So that's a thing to spend a little bit of time on. K-means clustering undergirds many of the approaches in machine learning that we're interested in. So that's a thing to kind of brush up on and make sure that you understand. Let's talk a little bit about a geographic example. We've gone through some of the ideas behind some of this stuff. I do think it's important to see how they pan out in geography. But again, I want you to really understand that geography is not the entire world of data analysis. That understand how these things work on non-spatial data sets is as important, maybe more important than knowing how they work on geographic stuff. So we're going to use a data set that I prepared here, the random forest classification data set. The link will be posted here in Canvas. It's going to be distributed as a geo package. We've mentioned this a little bit before, but a geo package is kind of one of my favorite new, still a little bit problematic data storage format containers. Supposed to be open, non-proprietary, and yet still support many of the sort of modern database kinds of operations that things like shapefiles just don't do super well. When you download that stuff, you can load it up and you can look at a classification by landslide. So we early on read a little bit about which counties in the United States went to which presidential candidate, and the idea was that if they differed by a certain percent, 20%, then they were considered landslides. So if they voted Republican a lot more than Democrat, then they were landslide Republican. If they were voted Democrat much more than Republican, they were landslide Democrat. So you can kind of look through here. Most of what you're seeing here are landslide Republicans, just because of the way the demographics work out. But if you kind of look closely at like the Bay Area in California, I'm going to point that out here, or LA, those are also landslide counties, but landslide for the Democrat candidate in 2016, Hillary Clinton. So 0 are non-landslide, 1 are landslide. You can see that just as Bishop had described in his book, and you had discovered in your assignment, indeed, more and more counties are becoming landslide counties. So I thought it would be fun to look at how well we can predict whether a county is landslide based on, and in this case, a really interesting one, GOP minus Democrat percentage in 2016. This is the exact field that we used to predict whether it was landslide, but essentially the way that we did the calculation was GOP minus Democrat, and take the absolute value of that, and if that is greater than 20, then it's landslide. But landslidedness is 100% calculated from this field. So how good does random forest-based classification and regression do? One of the things that I would encourage you to do is to look at the additional outputs that you can generate and keep track of those when you run this. There's a lot of really good information in there. When you run that, you get something that looks like this. So these are the trained features. You can look at the confusion matrix, which you can see down here, and variables, and you can see the relative importance of those variables in predicting the result. So in this case, GOP minus Democrat percentage was about 34% important. In contrast to the overall fit, one of the things we can do is we can compare this to ordinary least squares regression. This one's really interesting because our ordinary least squares regression essentially only has an R-squared value of 0.24%. So before we look at these numbers, I guess I want you to back up a little bit, and I want you to think about what we're looking at here. We have a variable that says by how much the Republicans won by per county. From that, we essentially determined whether it was a landslide or not, whether the absolute value of that was above 20% or not. And that was our prediction. Why, in this case, can't we figure this stuff out? It's super fascinating. The adjusted R-squared for the OLS is only 24%. If you want to try to play along, feel free to pause and see if you can come up with an answer. So the answer is very interesting, and the answer is that this is essentially a U-shaped curve. If you kind of plot this out, we essentially have values where this is the win percentage, this is -20, this is 20, and this is 0. Anything over there is a landslide, anything over here is a landslide, but effectively that's the same thing as if we were trying to, forget about that. That's the same thing as if we were trying to predict, find a correlation between something that broke down like this, right? What a classifier wants to try to do is fit a linear, to fit a line to this. And if I try to fit a line to this, I'm not at all capturing what's going on there. And that's effectively what's going on here, is our simple model doesn't work when we have a split along this line. So even something as simple as an absolute value transformation stymies OLS in a way that does not stymie random forest classifiers quite as much. One of the things that you can play around with as you do this, and I would encourage you to download that data set and run the random forest classifier. It's very easy to do. It shouldn't take you more than 10 minutes. And I would really like you to do that. Rerun your analysis. So one of the things that you can do is you can change the amount of training data that's excluded for validation. You can start cranking that up. What happens to your confusion matrix when you do that? The higher that number, essentially, the more error you're likely to get in your answer. But if you exclude almost all of it, then you're not training a very good model. So there's a bit of a test here. And then finally, I would try to add on to this a little bit here and try to construct a model on criteria of your choosing from the CHR data. Lots of interesting things in there: median income, health-related factors, population statistics. All of that stuff could be an interesting part of how you could explain whether a county went landslide or not. So that's where we'll leave things. We've kind of gone through a whole large gamut. This is a fairly long lecture. We've gone through a big gamut of different ways of sort of predicting categorical variables, from the very simple linear discriminant analysis model, which is good, the k-means clustering, which is often just as good, but is a little bit more flexible, slightly different intent, but still a lot of overlap there. We talked a little bit about principal component analysis, which is sort of tagged in here. You're maybe unlikely to use this a lot in the kind of work you use, but because it was related to the other techniques, I thought it was worth mentioning. And then random forest classifiers, which are kind of the new hotness. they work fine. They're easy to use. If you're more comfortable with using those than using something like principal component analysis or k-means, by all means, right? It's a perfectly good way of doing these things. So with that, we'll wrap things up. Thanks again for listening, and we will see you next time.